Hello everyone. In today's lecture, we are going to discuss about Bernoulli's equation, assumptions of Bernoulli's equation, and where this equation has been applied in real-time applications where you actually use. So this is what is going to be the agenda for today's lecture. So when I say Bernoulli's equation, this is actually derived from Euler's equation. So I will start with the Euler's equation. So Euler's equation is dp by rho plus g dz plus v dv. Okay. Now this is equal to a constant. So this is called as the pressure head. This is the velocity head. And this is the datum head. Right? Now we are applying this Euler's equation to an incompressible fluid. Okay, when I say incompressible fluid, the density cannot be varied. In other ways, in other words, density remains a constant. Right? We are applying this only to incompressible flow. Okay. Now, as a first step of integrating this equation, what we get? We will get P by rho plus, and I'm writing the third term here, V square by 2 plus GZ, right? So this is what we're going to get. So this remains a constant. When we divide this by G, P by rho G plus V square by 2G plus Z is equal to a constant. So this is the Bernoulli's equation. Okay. So what is the meaning or the physical significance of this Bernoulli's equation is you take a fluid which is flowing inside a channel, maybe a pipe. Okay. The pressure head measured at one instant, at one particular point, the velocity head measured at that point, and the datum head at that point. You sum up all these three values and keep. Suppose you're getting a value of x, and the same fluid flowing inside the duct, maybe the point where I have checked is this point, okay, reference one. Another point I'm taking, so the fluid flow occurs, and this reference point is 2. Here I'll mark. So this is reference point 2. At this point also, you please calculate the pressure head, velocity head, and datum head. You sum up all these three values, you will get another point value y. This value of x will be equal to y. In other words, both remains the same. So the sum of the three heads, pressure head, velocity head, and datum head at any point inside a flow will remain constant. This is what is stated by Bernoulli's equation. Okay. Now, how this Bernoulli's equation, like where all it can be applied. You are going to make some initial assumptions. We will see those assumptions. The first one is you're going to apply it only to an ideal fluid. Okay, when I say ideal fluid, the viscosity is negligible. That is somewhat, you assume it to be closer to zero. Okay, there is no real fluid existing which has got a viscosity equal to zero. You can say the viscosity is negligible. It's almost equal to zero. Like that you can say. And next, the flow is steady. The third one is the flow is irrotational. The fourth, which I have already stated, it is incompressible. Okay. So these are the four basic assumptions. Only on making this assumption to the fluid flow, you can apply the Bernoulli's equation. Right? So now we saw from where this Bernoulli's equation has come and what are all the assumptions or what are all the conditions after which you can apply this Bernoulli's. Okay. Now coming to real-time applications. Applications of Bernoulli's. The first one is orifice meter. The next is Venturi meter, and the next is Pitot. Okay, right. Now, what is the similarity between these three devices? I'll tell you. All these three are flow measuring devices only. Okay. The configuration or the physical structure of these devices only varies, but they are all used to measure the rate of flow. Okay. Now, the physical difference is compared to Venturi or Venturi meter, the orifice meter is quite simple, meaning it is just a circular plate. Okay. And it has got some holes inside it. Okay, so this circular plate will be placed in the fluid flow. That is inside the channel it will be placed. Okay, so that also I'll show you. Suppose I'm taking a flange. Okay, now the flow is occurring through this pipe or the duct. Okay, I am placing this orifice plate like this. This is how I place the orifice plate. Now the flow will be like this. Okay, now you can see the flow which was free to pass over this has got a restriction and it is allowed to pass only through this narrow passage and then it comes like this. So this is the vena contracta region. So I can say that this orifice plate, so this is the orifice plate. Okay, so this is orifice plate, which when it is placed along with the shaft, it has caused a restriction, and the fluid which was free to flow is now facing some restriction, and it therefore I can say that the velocity keeps changing. Okay, why this velocity has changed? Because the area of passage has changed. This was changed due to the positioning of orifice. Because of this only it has changed. Okay, now if I'm going to pressure the if I'm going to measure the pressure value that is here as well as here, definitely a variation will be noticed. Now I'm going to measure this using a manometer. I will take a simple YouTube manometer itself. Okay. So this is how I'm going to measure. So maybe I'm getting my mercury level here and the mercury level here. The differential head is noted. The difference in the mercury level was measured. Okay, so orifice meter functions like this. It is actually a circular plate which has got maybe two or three number of holes and it is aligned along with the diameter of the shaft. When the flow is allowed to pass through these holes, definitely the area of passage changes and therefore the velocity also changes. Right? And this change is measured by connecting one limb of the manometer on the left hand side of the orifice plate and the other limb on the other side of the orifice plate. The difference in this pressure head will give you the differential head. So this is how you measure the rate of flow, right? This is the simple concept of orifice meter. The next, coming to Venturi meter, this is again another type of flow measuring device, but the structure is slightly different. It will be having a converging section and then it will be having a constant area section that is called as the throat and again it will have a diverging section. So this is how it comes. Okay. Now I'm going to show you these three sections separately. This is the converging and this is the diverging, right? This is the growth. Okay. So we can say that this flow is undergoing a change here, and here preferably the cone angle will be in the range of 15 to 20 degree. So this will be the normal cone angle. And as the flow comes like this in this end of the pipe, you can see that there is a variation in pressure as well as velocity. And then inside this throat, it will be maintained. And as it again passes through the divergence section, again there will be a change in pressure and velocity. Okay. The difference between the orifice meter and venturi meter is the flow, that is rate of flow that you have measured using this device is more precise compared to that of orifice. Why I will tell you, since this has got a gradually decreasing section and then a constant section and then an increasing section, the restriction is not so sudden. It doesn't happen so just like that in a jiffy. So it is actually well organized. Therefore, there is no much suffering in the flow rate. So the value that you get using this device is more precise. Okay. But another disadvantage is manufacturing cost. So that will be more for venturi meter because that is only a simple circular plate easy to fabricate. So when we say cost wise, this is slightly costlier than the other one. So in this case, if you want to measure, you will only take the difference between the pressure heads in terms of manometric head. So this is the pressure head which is measured in terms of manometric head. Okay. So this you will get like V2 square by 2g minus v1 square by 2g. That is difference in velocity head will give you the pressure that is being measured. The next is whatever, okay, there's one more term called as coefficient of discharge. This is the ratio between the actual discharge and the ideal discharge. Whatever be the device which is used, the measure of CD that you get will definitely be less than 1. Okay. Now we are going to see the last one, that is a pitot tube. So this is again another device which is used to measure the flow, velocity of flow at any point inside a channel. So here, this is actually, you can consider a duct like this. I'm placing a bent glass pipe. Okay, this glass pipe is bent at an angle of 90 degree. So the flow which was occurring here is now allowed to pass through this small glass pipe. Okay, and let me measure at two different sections. That is point 1, which is away at a distance from this glass pipe, and other one is point 2, which is very closer to this glass pipe. Okay, now the level of fluid inside this bent pipe, let this height be noted as capital H, and here the level is H. Okay. Now we are going to equate the pressure values at 1 as well as section 2. We're just finding out and we are going to equate. These are the sections. Okay. Now we are using the same Bernoulli's equation itself. So your Bernoulli's equation is P1 by rho g plus V1 squared by 2g plus Z1, which will be equal to P2 by rho g plus V2 squared by 2g plus Z2. Right? Now, both are in the same levels only. The measurement point is this and this. So both are in the same level. Therefore, this you can cancel it off. Then what about the pressure value? In this case, it is going to be H. That is, P1 by rho g will be equal to H. V1 square by 2g remains the same. Coming to P2 by rho g will be this H plus H, right? It will be H plus H. And what about this V? This is supposed to be V2. This V2 will actually be 0. Okay, we are assuming that is our initial condition. This is to be 0 because here it was having a free flowing velocity. Now this is a very small diameter glass tube. So here you can say almost the velocity is 0. So therefore this also tends to 0. Right? Now I'll cancel away the light terms. Now your h is going to be v1 square is equal to 2gh. Right? So velocity will be root of 2gh. So this, whatever you get, this is going to be your theoretical velocity. And as I told you, you can use the coefficient of discharge formula, that is CD will be actual velocity by theoretical velocity. And in this case, your theoretical velocity is root of 2gh, right? So actual velocity is CD into root of 2gh. So this is how you determine the velocity of a flow using a pitot tube, right? So I'm stopping with this. So this class we have studied about, or we have learned about the basic principle of Bernoulli's equation, the assumptions involved, how to apply this Bernoulli's equation to different flow devices. So 3 devices we have seen, that is orifice meter, venturi meter and pitot tube, right? So next class I shall meet you with another topic. Any doubts? Kindly post a message. Thanks for your listening.